Which needs to receive that. I lock it up. I guess so. It's all for us.
All this stays. That's interesting.
That's right.
That's fine.
Ya
Hemos
hemos en ahí.
ha utilizado todo es la pantalla en
Okay, so now they are
I can't so it's a little bit random.
What we forgot to do is to send I forgot to send a reminder this morning. That's it was because we were not in the automatic cycle this time because of this weird thing with that we deleted it from the seminar. That meant that
It's also quite confusing when you set up queue list if you want to announce it, and the name it can be in left column or right column, but it's not sure which one is what. So I always loop them, but then it's unclear that I asked them, yeah, if they're in the right column, then they will be included in it. It's not obvious. This can be improved.
a list of
It's input into account, yeah.
One molecule has to be in another color.
Just the password.
I go to
I'll do the
excellent.
From biggest book, oh, I know that people have absolutely. Yeah. I think you have so this I didn't try for them. Nice to know. Let's hope they don't have a requisite of knowing. Director of the IPC, very nice night. I have to apologize because yesterday I had a meeting with you, and so on, but I couldn't make it. Sorry, I was for 2 days. So fortunately, I also get back today.
Thank you.
Sorry about that. Really sorry about that.
No.
Much more.
Okay, Ladies and gentlemen, it's my great pleasure to introduce you today to our esteemed speaker for the colloquium, Dr. Pedram Roushan, a distinguished member of the quantum AI team of Google. Dr. Roushan, he has an impressive academic background, having earned his bachelor degree in physics and mathematics from the University of Pittsburgh in 2005, followed by a PhD from Princeton University in 2011. In his doctoral research, he broke new grounds in the field, including the first ever scanning tunneling microscopy of topological insulators. Following his postdoctoral studies at the University of California, Santa Barbara, Dr. Roushan joined the pioneering team of Google Quantum AI in 2014. In 2019, Dr. Roushan and his team, they achieved a significant milestone by experimentally demonstrating the first algorithm that surpasses the capabilities of any classical computer. His current research is at the forefront of quantum computing, focusing on simulating novel condensed matter and the non-equilibrium physics using superconducting quantum processors. Today, Dr. Roushan, he will delve into the realm of superconducting qubits, a leading platform for quantum computation and simulation. And in this talk today, titled Quantum Simulation with Superconducting Qubits, we'll hear about the latest developments and achievements from his team. And this presentation is not only a glimpse of the current state of quantum computing, but also an exploration of the anticipated discoveries and timescale for these breakthroughs in the era of noisy intermediate scale quantum processors, the so-called NISQ era. So please join me in giving him a warm welcome. Thank you. Thanks for the kind word, and thanks for the invitation, and thanks everybody for being here. As mentioned, I'm a member of the Google Quantum AI team. This team started in 2014. This is our maybe our standard, in the spirit of California startup, is our garage picture. Lots of engineers working together, and in 2019, we demonstrated the quantum advantage, which I will talk about first. And here is the size of the current team, which we are focused on our mission, which is making a larger scale quantum computer in the next decade, hopefully. Let me start by saying something about the working force that we are using, the building block of the whole of this whole platform, which is Josephson junctions, came to existence in late 1960s by the work of Brian Josephson, which apparently was taking a course from Philip Andersen in Cambridge or Oxford, I forgot. So if you have two superconducting islands, and you bring them next to each other, so close to each other that Cooper pairs can coherently tunnel from one to another, then, each superconducting island can be described by a complex order parameter, which has amplitude and phase. If these two phases are different from each other, then you get a current going between them, a steady current going between them, which is its mass size is related to the sign of the phase Ginsberg-Landau phase different across the two islands. And if you manage to change this phase different in time, you can get a voltage developed between the two islands. And in the lab, this is how we make them. This is one superconducting island, is a island of aluminum. You oxidize, you get a few nanometer, maybe up to 5 nanometer of aluminum oxide, and then you deposit another piece of aluminum on it. So you make a junction. A few simple line of a couple of math operations shows you that this is in fact a nonlinear elements, nonlinear inductor, meaning that this inductance is proportional to this phase difference. And that's very significant because you can put this next to a capacitor, you can shunt this inductor, nonlinear inductor with a capacitor, and you make a LC circuit, the LC circuit which is nonlinear. The nonlinearity becomes significant because now you have a cosine potential rather than a linear oscillator, which has a harmonic potential, parabolic potential. So here is the junction that you see in here in tiny details in here. We are coloring it up for some reason. And then here's the capacitance I mentioned. So you have an L and C, and you're making a resonator. The resonator, which now thanks to this cosine potential now, have the level of spacing non-uniform, meaning that you can address whatever level you like, and essentially without getting bothered by the higher level. So you're in this cosine potential, you might get up to 15 levels or so, but you can address them selectively as you like. Before going further, maybe you wonder why these sizes we are choosing, and where are we standing in the spectrum of possible sizes, or why this size, why not bigger, or why not smaller? Well, first, let's look at the maybe wavelength, sorry, maybe look at the frequencies of where we are standing. So if we are dealing with aluminum, so we have to be much smaller than the size of the gap in aluminum, so we don't get quasi-particles down to that. And then there's another limit set by the size, the temperature of the dilution for each and what is feasible to achieve. So you want to be cold, so the aluminum superconducts. And then the frequency we choose is above that. So the quasi-particles that if exist at those frequencies are not at those base temperatures are not bothering you. So that's where the kind of the energy scales comes in here, and that translates to these sizes. But of course, you can always, why not move to one side or the other? And there are many different reasons. Well, the simple argument is based on KBT. You just want to be somewhere safe in here. You can make them bigger. Well, of course, it's not good for KBT, but it's going to get cheaper. It's not clear you're going to achieve the same coherence. You can go much higher, but it's going to be more expensive and probably more difficult to make them smaller and smaller in the lab. So at the end of the day, maybe as a mixture of historic and practical reasons, we are dealing with these sizes, and they look like giant atoms. They are visible with naked eyes. But many of you could be familiar with atomic systems. This is another way of doing the same physics, with just everything is 1,000-time difference. And so it shows that you can even work in a very different range of parameters, and you can get things to work. So you don't necessarily need to be here. You can just manage to get your parameters worked out in a different regimes, but then become a big hardware challenge. Each limit has its own hardware challenges to get it to work, but is all feasible to work one way or another. So after you make one of these nonlinear resonators, you can put them together. You can stack them, and you can put them next together. This is a picture of a array of 1x9 1D array of qubits, nonlinear resonators, which, since most of the time we're only dealing with the lowest two levels, I could call them usually qubits. So when I say qubit, I mean this nonlinear resonator object, this physical object. But yeah, you should not be confused what computer scientists think about. Well, the computer scientists think about a system with two levels. Ours have more levels, but we can confine the discussion to only the lowest two levels of these nonlinear resonators, hence the word qubits. So here's a picture which is maybe a decade old, so I can show it. It's done at UC Santa Barbara. I can show it without getting fired from Google. This is as far as you can go in 1D structures, and the colors are just Photoshop color, so you can see what functionality of each part is. The capacitance are not the cross shape that I showed on the other slide. It's just this strip of aluminum. And the junctions are followed by them. They're very, very small to see. And then there is this dark green color, two squares next to each other. That's the object we call them couplers, which is essentially another nonlinear resonator of qubit at much higher frequency. The virtual hopping to these couplers allow direct coupling between the two qubits. So what you're seeing is a pattern of aluminum made by lithography on top of an inert substrate, which could be sapphire, which could be, I think in this case is sapphire, but currently we use silicon, very pure silicon, just to hold this aluminum sheet together. On top of the qubits, you see a meandering line, which is a linear resonator, and the AC Stark shift out to these qubits would shift the frequency, resonance frequency of these resonators, and you can see the state of attached qubits to them. So if the qubits, if the associated resonator shifts by a few megahertz on top of its gigahertz frequency, you would know that if its associated qubit is occupied or not, if it's 0 or 1. So by sending one signal in and out in one shot, you would know the state of 9 qubits, because each of these resonators are slightly different. If you pay close attention, you see they are slightly different in length. They are not the same length. And that's sufficient to space them in frequency. So we multiplex in frequency domain, and you can see the state of all the qubits in one shot. And you can repeat the experiments maybe by the rate of 10 kilohertz or so. So you get bit strings, 10,000 of them in a second. Well, maybe it was too long of a babbling about how to make these objects, but maybe that's sufficient to know that if you put them all together, you have a Bose-Hubbard Hamiltonian, realization of a Bose-Hubbard Hamiltonian. By that, I mean that if you excite one qubit and you say, where does my excitation goes? It goes e to the I HT, where H is given in here. So you have a on-site potential, you have the hopping term, and you have the Hubbard U term, and some higher order terms. And you can see the size of the parameters, and we can control them in time. If wherever you see a wire coming from below means that we have control over the states of these qubits. We good? You guys can ask me questions whenever you like. So this is the outline of the talk and things I want to cover. First, we talk about the beyond classical experiment, and then I would get a little more towards something more useful. And, we say what can be done with current existing platforms. And then if time permits, we get into the study of phases of matters and experiments that we did. This slide is for those who like to take a snapshot. So you see all the references. I would not repeat the references later on. The beyond classical experiment, which was originally called supremacy experiment. So what is this about? It came, the word supremacy is attributed to the paper in 2012 by John Preskill, which says if this processor is good for anything, let's just get them to do something, well-defined, well-posed question, but let them to do something that at least we can see they can do something quantum and that classical computers cannot do. Before they come and solve global warming and cancer and all those issues, let's just see if they can do anything at all, okay? Why is that interesting? Because this is, my younger colleagues tell me I have to use these things, which I don't know what they are actually. Well, qubits are faulty. The closed quantum system I wrote is only an approximation. It's an open quantum system. There is a decay of the qubits. They are falling and failing left and right. So can we do anything with them? And that's the essence of the first experiment. Pose a problem and then try to do it. So the whole beyond classical experiment sits into two pillars, which I'm about to show you evidence for it. One pillar is high fidelity in the control of the experiments. You really, it's not very hard to create a complicated motion. You can toss your keychain up in the air and you get a complicated motion of the movement of the keys. But that's not difficult. You just have to have good control over it. Otherwise, making some mess is not difficult, right? But then another notion is notion of ergodicity. We want to be sure, what do I mean by ergodicity? We want to be sure that the dynamic that we created is exploring the nominally available Hilbert space uniformly. If there are symmetries in the system, which prevents you going from certain part of the Hilbert space, the computational space, then the problem is not as complicated as you think. It can be simplified, can be run on a smaller computer and whatnot. I'm using these two iconic pictures from moving a billiard ball in a circular table, which in one case you can see is avoids certain part of the table, avoids certain part of the computational space. no matter how long you wait. So therefore, this problem is more simplified than that space shown. But in a stadium type billiard ball, if you wait enough, it goes everywhere. So you need to know exactly, you need to take every piece of a space into account. I would not show evidence for that, only tell you that we do random circuits. So we're going to assume random circuits, but they're more than we assuming. It's going to go ergodically over all available Hilbert space available to it. But I will show you the evidence for fidelity. But you might be a bit unsatisfied with this line of logic, right? How do you know that we have done something which couldn't be done on classical computer? How would you know that you have tried hard enough? And the answer, truth to be told, is we don't know. We don't know. We tried our best. We think there is no classical algorithm can be found that would, but many nights we lose sleep because we are worried that something pops on archive the other day, which says, oh, we could do it in our laptop or whatever. It could happen. There are strong evidences, many theorems, but the theorems, again, written for closed dynamics. So when you have noise, you don't know how things get simplified. But the best of our evidence is that we have not found a black swan, so probably doesn't exist, but we cannot rule out the existence of that, okay? So this is truth to be told, and I show you evidence and how we are trying to convince ourselves more, but it's very different from the mindset of saying that this has been proven to be computationally difficult. As I said, there are lots of evidences, but at the end of the day, you're dealing with the instance of a circuit. You say this circuit and I got this value. How can I be sure it couldn't be done otherwise? The answer is captured in this thing, which probably you're familiar with yourself from Karl Popper. Well, you never know. Well, as I mentioned, the problem is well defined. Is where you have initial state, is a product state, and you evolve it with some unitary evolution, and you sample from the highly entangled wave function, which generates at the end. So on a grid of qubits, which was 6 by 9, but one of the qubits didn't show up to work, you have 53 qubits. And on this grid of qubits, you apply sets of operations, single qubit rotations, 2 qubit operations, which all well known. I can share with you what they are exactly, what each unitary is. And you get a wave function, which is lives in 10 million billion dimensional Hilbert space. And you are sampling bit strings from it. In this case, the bit strings would be 53 digits long. And you're claiming that you're doing it with high fidelity, as I will explain soon. As I said, there are theorems that are showing that this problem is hard, but they are written for unitary evolution. They don't take into account the effect of open quantum systems. So that's the well-posed problem that we are about to solve. And I will show you as number of qubits or as a function of number of cycles, how well is our fidelity and is beyond something, sampling from distribution given this fidelity is beyond capability of classical computers. Well, I have to compare the bit string from with an exact number. So we just use these Shannon entropy type of fidelity based on this Shannon entropy, which means I get a bit string. What is the probability of getting bit string? So when you go to a classical computer and compute the probability of that bit string, and you compare it with what you got, and then a bunch of normalizations and whatnot. So to be sure this number goes between 1 and 0, it tells you that what is well your fidelity. But underlying physics is that you could measure, you have a notion of what should be expected. So you need to use a classical computer. If you ever came to the paper and saw the equation 1 being different from what I wrote here, the equation 1 there is written in the limit of large systems and assuming that ergodic exploration of this space. So it's the same thing taking into this under these two assumptions. Okay, there's one piece of information I have to tell you. As I said, we are going to layer of, maybe you didn't pay close attention. So you have layers of single qubit operations followed by these colored ones, which are 2 qubits operation. But as soon as a qubit want to get involved with another qubits in a 2 qubit operation, you have You have very many different ways of doing it. In what order you can do it is different. You can see there are different orders that can be done. So it happened that one order is very computationally hard, and the other order, if you go there, if you apply your 2-qubit gates in this order, it would be computationally simple because of the way that it propagates entanglement in the system. So we can take advantage of it, and which these two patterns are just different by the order you apply the gates, and you assume that there is no temporal correlation between errors. So these operations are done more or less with the same fidelity, and you can have a notion of fidelities even in the regime which are computationally very hard, right? So left and right is the sequence of the gate are slightly different from each other. We start by not applying the gates that connect left and right of the qubit. So we run 2 experiments on 2 sets of qubits without connecting them effectively. So in this case, the system is composed of 27 qubits or 26 qubits, is rather computationally simple, or and you can compute the fidelity as a function of depth or cycles or number of qubits. That's not computationally hard because the grid is not that big, because we manage not to connect left and right of the system. You can go a slightly more advanced version of it, which is you connect left and right, but not all the cycles. You skip maybe 5 cycles in the beginning. You don't connect these 2 patches of qubits. And then in the later cycles, you connect them. That's the notion of elided. And in this case, also, you can compute this in the verifiable, classically simple sequence of gates. You can compute that, but on the other side, it's already getting difficult. So when I get to the full circuit, now it's impossible to do it on your right side. But here still you can do it because, as I mentioned, this sequence of gate is more is manageable with a classical computer. So I want you to believe that I can do the same with the same fidelity. I can do things on that side. Because if I change the order of the gates a little bit, hopefully the fidelity is not changing. So I don't have a proof for it. That's a matter of belief. But given the algorithms we could use, this is the time it takes. Okay, so it's getting really, really impossible to do it on the right side. But you might say, well, I mean, your classical computer is doing the full wave function when your quantum computer is filled with error, and you have to give classical computer a break. You have to put them on equal footing. You can simplify that. You can ask your classical computer to also put bit strings out which have errors in them. And the computation gets simpler. So by exactly that factor of fidelity, that's the gray numbers. And even after this, in 2019, we claim to get the bit string with the fidelity which we are claiming we have, it takes 10,000 years. So that was the state of the art when we claim outperforming a classical computer. And that's our evidence for it, and rests on certain assumptions. As you know, probably things changed, and numerical methods improved, experimental improved, and exactly as we predicted. One exponentially gets harder, another one struggles to catch up with it, but it polynomially catches up with it. Our result was outperformed by 2 results from the groups in China, but then very recently we outperformed them. So we are back on top. But numerical methods improved too. So you can see that what I just claimed, it took 10,000 years. We can do it ourselves now in 6 seconds ourselves. But the new claim that we have is that the last point, it takes, it takes a long time. So the boundary moves, and it's not surprising. Numerical method gets better when you focus on it, but it's not about exactly where the boundary is about how one scales versus the other one, which gives the quantum processors their power. Okay. This is interesting, and I want to now provide a little more evidence for the notion of ergodicity I said. Let me show you a simple intuitive way of showing ergodicity. If we change one of the gates in this sequence, if we just choose, let's say, this single qubit gate, we choose it, we are making the simulation or the implementation different from each other. You can flip this on the experiment, or you can flip it during the simulation. What happens is that the order of the fidelity you get drops by 2 orders of magnitude, meaning that it's so sensitive on the accuracy of these gates. These fidelities are robust, but also is very sensitive on knowing exact circuits. It's not that, if you get the wrong bit string, somehow the fidelity cannot go lower than that, because what are all the possibilities? The issue is that the possibilities are so many that if you get the wrong bit strings, by just having one single gate in one of the cycles different is sufficient to ruin your whole circuit. So everything has to be closely. Now is a test to see how old you are. In the movie Amadeus, Salieri says that the composition of Mozart is so accurate or so precise that if you change one tone, maybe I had it written, you change one tone, the whole composition falls apart. So that's a supremacy in the classical music realm. And now I'm showing you the supremacy by changing one tone in the quantum realm. Most people don't know which movie I'm talking about. Well, okay, let's get more serious with this notion of ergodicity. Well, we want to measure chaos, ergodicity in our system. Okay, the first thing comes to mind is drawing analogy with classical chaos. If there is a disturbance happening in Brazil, what are the chances that this weather system is chaotic, that you are going to get a tornado in Texas, as was explained in the original paper by Lorentz? Okay, let's do that. So we get 2 initial states. They are slightly different from each other. And we say we evolve them under our weather system or Hamiltonian, and we see how much overlap they have later time. A very simple math shows you that evolution under Schrödinger equation is overlap preserving. So these things, whatever overlap had initially with each other, in the future, they're going to have the same overlap. So that is going to fail drastically. I'm not going to give you anything. There is no Lyapunov exponent on how these 2 vectors are diverging from each other. That's sad. Well, the simplest or the next level of things that you could come up with is better explained in the Heisenberg picture. You have 2 operators. These 2 operators initially they are commuting with each other. They don't have any overlap with each other. Our wing operator is the butterfly, and V is our vortex. So the wing flap of the wing does not create a vortex at the position of the other operator, which could be a measurement operator. But as states are fixed and the operators evolve in this picture, there would be, in the future, there would be non-commutation. The commutation become non-zero between V and W. And that's the Heisenberg picture. And that is the notion of ergodicity that we are going to see how much information is getting scrambled. If I translate this picture to where we live, which is the Schrödinger picture, it means this is the sequence of the operations you have to do. We're just translating that physics. It means you operate under U, you have a perturbation, you have a flip of a butterfly wing, and then you evolve backward, and we're putting these in the correct place and whatnot. You get 2 vectors, 2 states that the overlap of them is exactly showing you how much non-zero is this commutator, okay? So here is a simple implementation of it before I show you the one that we did for our quantum supremacy circuits. You evolve under U, and you want to measure over qubit 1. You put a perturbation butterfly on qubit B, and then you reverse the operation, and you see what you see. You ask, what do I get in here? How long it takes. And here is before and after some error correction of the signal. This is the measurement happening on this qubit. Is called out of order time correlator measurements. And you can see that indeed you have to wait for a certain number of cycles. And then after that, boom, the front of this entangling wave, if you like, or front of this disturbance, scrambling hits your measurement qubits. This butterfly, I think this butterfly is moving over sites. You always do measurement in the first qubit, but the butterfly, different colors associated with where was the position of the butterfly. As this butterfly moves further and further away from your site of measurement, it takes longer time for this frontier to get there. So it's very intuitively understandable. When you get there, boom, it's a hit or miss, right? It just drops the value of out of order time correlation drops to 0. And here is when we applied it to our beyond classical circuits, the top row. You can see how this scrambling propagates in the case of ISWAP, which is close to the gates we use for the supremacy experiments, and how it's distinct from the case of the square root of ISWAP, which is a different gate, which is slower propagation speed. So note that by 15 cycle, every qubit is, roughly speaking, is entangled with every other, with the probe qubits. And the other one, even up to 22 cycles, is still, you can see that the entanglement has not spread across the sample. And if you recall this, in the supremacy experiment, we stopped somewhere up cycle 16 or so. So that's an evidence that, in fact, ergodic behavior has been propagated across the CPUs in this case. Okay, now I want to shift gear. Okay, maybe we don't get even to this last part. Okay, so as you are sensing it, it was all aspect of a contrived problem, the problem of sampling the bit string. Although it excites computer science community very much, it always fails to excite the physics community on why you did it. So I'm going to explain two physics problems that we could solve, and that indeed hit a resonance with some members of the quantum community. Well, the first problem I'm about to describe is about formation of bound states. Okay, so if you haven't heard about the word, it's not a big deal. I explain to you what it means. You put 24 qubits, you put them in 1D closed rings, and then you excite a couple of the qubits next to each other. You can think about it of a magnon excitation in a spin chain. And the claim is that these excitations remain together. They have a form of bound magnon states, if you like, meaning that these excitations are together, meaning that when you come and look at the wave function later on, every time you see, you get a superposition of all possible bit strings in which in all of them, the excitations are adjacent to each other and they are not, there is no distance between them. So that's what I mean by bound state, and I'm about to show it to you. So, okay, what is this dynamic? How from initial state we go forward? The Hamiltonian we chose is XXZ, I think probably, forgot, maybe delta is equals to 1, so it's the Heisenberg model. And this has been extensively studied in cold atom groups, particularly by Emanuel Bloch's team. And they have seen the bound state in this model, and they maybe even a decade before us. So we're going to do a little cheating, and we are going to pick up this same Hamiltonian, and we do it on the Floquet limit. We are not going to be on the Hamiltonian limit. We are going to apply a sequence of 2 unitary gates, which could capture the same physics of having hopping and interaction, ZZ interaction terms in them. So you can see how this Hamiltonian is associated with what we have done. And there is that proves that this Hamiltonian is also, this Floquet dynamic also have bound state and whatnot by Aligner and by Tomasz Prosen. So what do you see? So first, let me show you the evolution, right? These are the unitary gates that we apply, one cycle after another. In the limits of theta and phi being very small, you essentially get the Hamiltonian back, but we're not going to confine to that small angle limit. So here's the bit strings you are getting. First, let's just excite one qubit in this ring and then see where does it go as a function of time and space. And qubit 24 is next to qubit 1. If there is one excitation, one photon, there is nothing for it to bound into. So it has a very happy cat walking or whatever you call it. It's just going to be a diffusing, propagating over this lattice without interacting with anything. It's a single particle physics. And it forms a very nice interference pattern. But as soon as you have two, you can see that rate of propagation is getting smaller and is mainly they're staying closer together. And I would analyze this more in a second. And you have more and more, you can see that it seems they are staying together. So the intensity here is where did I find the photons? And it seems they're staying together and they have less tendency to spread, although there are cases that, of course, it seems they break and they go as fast as single excitation would have gone. So it becomes clear if I filter these data a little more and just focus on the bit strings in which they are together. As soon as I do this filtration and I show you only the cases that the bit strings are together, you can see the two excitation case is very much similar, gives a very similar pattern to single excitation, meaning that the center of the mass of these two photon excitation is moving very similar to the case of single one, and forming an interference pattern. It only propagates slower. And you have 3 and 4 and 5, it's showing the same physics, except it's just the velocity of its propagation is just getting slower and slower. So, and this is all according to theory has been written by Igor Aliner. So there is nothing that theorists didn't know before us. But here it comes something that is novel and you can really easily do in the experiment that you cannot do easily in the theory. Well, the physics that I was saying, the formation of bound state and the evidence of it theoretically is coming from integrability of the Heisenberg model. It's been a century ago. Bethe-Ansatz integrability is in fact originated from that, showing that that model is integrable. And this is a very comfortable land for theorists to work with these integrable models. But integrable models are very small subset of all possible Hamiltonians. So it's more natural and more easier not to have integrability in a Hamiltonian that you can realize in the lab. So it's exactly the opposite problem of this Achilles heel, that every part in its body, every random Hamiltonian is not integrable. It's just very fine-tuned to this corner, which was integrable. So you don't need to have malicious intents. Every is more natural, in fact, to break integrability than not to break it. So you put 14 qubits in a ring, that must be integrable, but you connect every other qubits to a new qubit, to a different one. And that would break integrability by going from 1D to quasi 2D that you're going. And you could get 4 times more Hilbert space by going that. So after every 2 qubit gates that we have in the ring, we are going to add these operations which connect you to the outside. So any self-respecting theorist would tell you that Fermi golden rules would predict that as soon as you start doing this procedure, as soon as these red bonds become non-zero, very quickly your bound state is going to go to thin air and is going to disappear. Okay, that's what the theorists told us, and we're very happy to test them because they can only do very small perturbations, and in the limit of small perturbations they can work, but we can go easily beyond that. I guess by the tone of what I'm saying, you can guess that that's not what we figured out. So here, what I'm showing as a function of cycles, the vertical axis is some notion of how the bound states stay intact together. If ideally you want this line to be flat. As you perturb more and more, so if you don't do any perturbation, that's your baseline, top line. As you perturb more and more, this is the angle of connecting to the quasi 2 dimension, bound states goes away. Okay, but what matters is how long it takes to go away. So what magnitude it takes to go away. So this is the magnitude of the perturbation in here. How strong is your perturbation? And this is the same data. I'm just making a cut here and here. And you can see that the bound states are staying together with the perturbation, which are as strong as the dynamics in the system. So it's way beyond the small perturbation limit. The limits that perturbation theory works, you can see the bound state stay intact. And only when this connection to the quasi-2 dimension become very strong is that the bound state immediately goes away. Okay, so there is certain robustness to this integrability breaking, which you could not see coming from if you were thinking about Fermi golden rule or simple implementation of Fermi golden rule. I'm showing you the same physics in momentum space. We can do something that ARCUS people have been doing, and I didn't go to the detail of it. But this is the same picture in momentum space as a function of perturbation. Perturbation gets stronger, or integrability breaking gets stronger. Eventually, the band of the bound states goes away, okay? Not surprising. But again, look at the rate that it goes away. If I was wise enough to ask theorists to put a line before we took this data, this would have been the line they would have drawn. But this exactly takes much more strong perturbation for these bound states go away, as if we are measuring the, I don't know, some full width half maximum, showing how robust is this band of bound states. Okay, here's my claim to fame. This is this work. We just put this work on arXiv, and then without us telling these researchers anything, 1 year later, we woke up one day, and these two groups very close to each other in time. You can see time there. It's maybe 5-10 days apart from each other. So that's what I'm saying about engaging with the community. They try to explain the physics, and it's more beautiful that they don't even agree with each other. That's very satisfying to me, that they're concurring to what we are finding in our limit, which admittedly could have been done on a classical computer, but we are bringing to their attention this problem of what happens when you break integrability. One approach is heavily numerics, another one is very much focused to study the case that we did, and they come with conclusions which agree with us, but when they try to extrapolate, they got a little disagree with each other, which I love. So this is usefulness at the moment. That's how that's I'm very satisfied with that. Okay, maybe this would be second and last example I can talk about. So okay, what are the other cases that we can get community engaged? And this is in the very similar vein is about non-equilibrium dynamics. And let me explain the physics of what we are seeing here. So the simplest modification to the diffusion equation is adding this extra term in here. And you arrive at the stochastic equation, which is known since 1980s, which is very successful in explaining how interfaces grows, how okay, too much. How coffee or tea stain on a piece of paper propagates, what is the shape of this, what is the fluctuation that you're seeing in here, how a fire in a forest propagates, what is the shape of the edge, and what is the variance in the edge that you see in here. This equation has been very successful in explaining it. It's a bit difficult to solve it because this lambda parameter is positive and it keeps getting diverging. So there is a conjecture, which is not our business to prove it, disprove it, that if you deal with the ballistic deposition problem, let me just go back. If you go to ballistic deposition problem, the universality class and the physics that you see over there is the same as solving that differential equation, okay? This is an unproven conjecture. We leave it as it is, but it's very convenient to work with. So the concept of ballistic deposition, as you can see, is randomly you choose to have snowflakes coming down. Whenever they see something in the left or right, they get stuck. And then you can take a picture of this. There is a height profile, there is a correlation length in the height, and there is a fluctuation of the height and whatnot, and you can analyze it. And that is essentially, it's been claimed that capture this physics. So it's good to have easy numerics in hand. But the conjecture that we care about, and maybe I give a spoiler that we're going to refute it, is that the dynamic in a quantum 1D Heisenberg chain follows the same universality class as this Cardor-Parisi universality class. Okay, that's the conjecture that we care about. Fully quantum world has nothing to do with this physics of the, well, the equation is Heisenberg equation. Here is something that put together by Cardor-Parisi and Zahn. And the claim is that the dynamic falls onto the same universality class. Let me be more specific. Here you can see height. So you can take the derivative of the height with respect to space. And you can imagine in a 1D magnetic chain, you could have a profile of the magnetization at an instance of time. S of z as a function of space and time. So if you define this quantity, which we call relative height at the center, you measure height at the center and you subtract its asymptotic values at two ends where L goes to infinity. And then you compare it with magnetization transfer, meaning that how many excitations, how many magnons jump across the center line, what is the number of magnons or magnetic excitations on the left versus the right, and you subtract them as a function of time. It's called transfer magnetization. The claim is that this transfer magnetization and these two quantities are indistinguishable in terms of the universality class. Two stochastic variables doing exactly the same thing. That is the claim. There are numerical evidence for it, well, indirect, I would say, and there are experimental evidence for it. There's a little more complication to it. When you're constructing this quantity, the initial state matters. If you're depositing on a flat surface, if a snow falls on a flat surface, the universality class is different than if a snow falls on a surface that has a slope, okay? We're going to take that into account, and that even didn't save the conjecture. Okay, so this is the preliminaries, but let's see what we do in this work. So we get a chain of 46 qubits with and we choose a value of mu is a number, maybe 1 or 5. With this probability, we excite the qubits in this side. We flip them a spin up, let's say. And with the same probability, we put them a spin down. So we don't follow a harsh domain walls, but we are making something which is mainly up in here and mainly down there, let's say. Okay, so that's the initial states that we make. After you choose mu, that's set. And as a function of time, you would measure this transfer magnetization. You say how many yellow jump to the left, or how many, well, my left, how many blues jump to the other side. Okay, that's the transfer magnetization. And you repeat the experiment over and over again. Maybe that axis is easier to see, that there is a probability distribution of what they are, and we record them as a function of time. And then some post-error selection tells you that the actual value goes down. It's hard to see in the linear scale, but you can rescale it and get the same statistics out of it. Okay, so that's the data we are about to get. And these are instances of these data that you see. For instance, in this case, mu chosen to be infinity. Everything on one side is all up and the other side is all down. And then you evolve it for one cycle and you sample it maybe 10,000 times. And I'm showing you one sample. And gradually you see that it goes to some mix of up and down. And you repeat the experiment over and over again. And you get maybe, I don't know, you get maybe about 1 million bit string times in here, which maybe 1 over 1,000 of them have the correct number of excitations that you preserved, and you change the value of mu. The challenge is that you can see these initial states are smaller, mu's have less contrast, but the conjecture is also correct. It has to be examined in that limit, which takes longer to thermalize if you wish. So we are going to make these histograms of how many excitations pass the middle line as a function of time, and we are going to explore those histograms and extract the high moments of these histograms and explore them to depth. Okay. So here is simple things. What is the mean and what is the variance of these histograms? And I'm showing you here for various values of delta. If you remember, delta was an isotropy term in the Heisenberg Hamiltonian. These are literature that exists by many, many people, so I'm not claiming anything new in here. This for various values of delta, getting diffusion, where is it? This diffusion, subdiffusion, ballistic has been extensively studied. We are just trying to show that we are a member of the club. So when we do something other people have done for decades, we can do the same. When you get to variance, that's a little more charming. We get superdiffusion is called, I forgot. We'll get to cert, which is consistent with the Cardar-Parisi-Zhang universality class. So far, so good. And it's consistent with the work that incidentally also done by Emanuel Bloch's team. So we are cheating again. So we're all getting the same results. So far, so good. And then, you want to claim victory, say, okay, we agree with the community, that's all good. But here I will really want to bring, then you sit home, you turn on TV, you watch commercials, someone who has been very influential in your life tells you that, well, you have to do more. And it's not someone you can ignore. So when you want to study universality class, he suggests that we have to look at the higher moments, okay? And I really want to bring this to focus. When we say a stochastic variable belongs to universality class, what do we mean? How many moments have you go and check to claim it? If it works up to moment 13 and fails after that, what can we say? So these are the questions that no one paid close attention because it's very far out of the realm of theoretical physics. Is very challenging, and numerically also is very challenging to do these non-equilibrium dynamics. And there is no answer. We always assume that if we check the mean and variance and maybe kurtosis, what's the third one? Skewness is going to be fine. But now, for the very first time, we are going to kurtosis, and we could have gone higher moments if we had the patience. And we are really asking a more, well, I can show you what we found. But more interestingly is the question for our friends in theoretical quantum statistical mechanics, that what is actually the definition of universality, and how should you really think about that? I think that is the value of this commercial is, like what is actually should be done. That's actually, I think, it's an interesting point. Well, okay, so this is the definition of a skewness from and kurtosis that we are using. This should be maybe called excess kurtosis, but that's minor detail. So same distribution. If you have enough confidence, if you have enough data points, you can get these higher moments, which are pretty challenging to do. And let's just focus on this one. We are showing you the values of skewness as a function of cycles for various values of mu. And as mu gets smaller, as I mentioned, the conjecture is about getting mu to 0, which is rather harder than the other limit. As it gets smaller, you can see this skewness seems to tend to 0, okay? So what is the prediction from the KPZ? The KPZ conjecture, regardless of you start with, say, is a flat ceiling or is a tilted ceiling, two values are different. Nevertheless, they are in this range. These are the values, I think 0.22 and 0.30 something are the values, and this is the values that atomic system, the cold atom experiment claims. But it seems we are not seeing that. It seems it's going to 0. Well, you might say, well, you didn't give it enough time. Maybe if you wait infinite time, and take mu really to infinity, maybe it doesn't go up. So you see it's becoming a challenging question. The actual question to ask, or the thing to realize, is that taking this initial imbalance to 0 and taking time to infinity are two non-commuting limits. And the order that you take these limits matter. And when you think about it, the conjecture says that you should take the mu to 0 first and then time to 0, time to infinity second. And this is the wrong order of the taking limits. So keeping this in mind, we can collapse this data based on some heuristics. And you can see how this data collapses in here by scaling properly. And it tells you then and knowing this, this argument, you know which limits to look at. So the correct limit to look at is the limit of close to 0 in this units, in this axis. And you can see, I don't know if you, well, again, I want you to believe that the value here is close to 0. Still, you can get more and more data, of course. But it seems that this tends to 0. And in fact, the atomic system in a sense is correct, that in the other limit goes to that, but that is not the limit that we should study it, and the order of the limits matter. So our value of skewness is disagree with the prediction of the KPZ, the correct one, which is this big range one. So we are finding values disagree with that, so we can reject KPZ. Unfortunately, we co-author paper with these people who have their own theories, which nominally I would have ignored, but since they are co-authors in the paper, I have to examine their theories. So we get experiment 0, which agrees with their theories. Oh, I'm on record. Okay. So we go to kurtosis because we reject KPZ, but there are the other contenders in the room. We go to kurtosis, and you can see that the kurtosis may be more aiming towards 0, and you can be sure that it's not falling to KPZ or the other two theories that I mentioned over there. So, well, for sure we can, well, okay, this is the data. I would say for sure we can rule out the KPZ conjecture. And also, it seems we can rule out the other conjectures, well, let me tell you a little about these models. These models are not the explanation these models are written with the mindset of what is the essence of this physics that can be captured that is leading to this similarity with KPZ physics. And you can see that you can take these models to these limits, and at least the nonlinear fluctuation model is failing. The other one has some chance. But nevertheless, the true explanation is still waiting. And you can see this is now going a little beyond what theoretical physicists have been seeing. And now we can leading the way in this study, and we can say something that's hopefully exciting to them. Okay, well, good. So I think we're going to stop here, no? This is going to go 10 minutes at least, each of them. Huh?
Yeah, maybe it's less.
I think they're falling asleep.
Pity, but okay.
Yeah.
Maybe there will be chances also after
Yes,
this
yeah.
to
Yeah, right. But maybe we give the rest of to questions.
Okay, let's first thank Pedram again. And take some questions from the audience. Daniel?
In the initial experiment about supremacy, one of the key important things is that all the qubits are highly connected to each other. Now, in all these experiments, when you do a chain, use the same type of architecture for the microprocessor, or do you have something different?
No, it's the same
chip. Yes,
chip.
how are you sure that the qubits are not talking to each other if they're in a chain, in a loop?
Good question. In the supremacy experiment, the qubits are only, or the grids that we make, qubits are only nearest neighbor coupled. In this grid, the crosstalk in the chip is minimal. Maybe every qubit is coupled to its neighbors, not beyond that. Okay, but the scrambling experiment I showed is as a result of dynamic, they get all entangled coupled. but the operation is local. This operation is all locally, so you can deactivate the qubits and no one sees it. On the ring experiment, on the bound state, you come and you carve your ring by canceling other qubits, by just sending them to different frequencies, and they are there physically, but their resonance energies are so much off that you don't need to worry about.
The question on the last experiment you described, and the role of fidelity in there, and also in comparison to the atoms and because first here in this fidelity played a big role, right?
Yes, yes.
And in the second one, I wonder if the fidelity of your gates is different. You simulate different dynamics, right? All of them are dynamical systems, I would assume, but it's possibly they are different universality classes depending on the gate fidelity that you.
No, I would not attribute that to gate fidelities. Truth to be told, here we are using a gate which is the fastest scrambling one, so we want to scramble faster. The other one we have to that delta of the Heisenberg tells you what gate to use. So we have to start from somewhere that theory shows interest. So the gate is slightly different. But on the grand scheme of things, the gate fidelities are, at the end, they're not that different from each other. Up to certain cycles that we could do, we did numerical work, and it's consistent with our experiment. So yeah, fidelity is not going to lead to some.
Okay, so are you saying that it's for all? So theoretically, you could have fidelity 1. You will get a certain dynamical system belonging to universality class, and then if this fidelity is changed, it is expected to remain in that class, or
Okay. Yes. Yeah, fidelity does not play a role. In fact, it was a bit insensitive to fidelities. Yeah. Let me see if I can. There is a slide which sometimes maybe not. Okay. Up to shallower depths. Okay. So this is simulation, which stops sooner. And you can see that we see the same physics. This is noiseless simulation. Yeah.
So the resonators are not two-level systems, as you explained. Is there any use to the extra levels that you?
Yeah, I didn't show any usage in this presentation. Well, I showed maybe very indirectly that to realize these gates, yeah, I guess that's not. To realize these gate operations, to get this phase accumulation in here, you kind of rely on the dispersive shift from the other levels. That's the third level, the next level we are not using. So they play some role in there. But also, I encourage you to think about what can be done. There is a good reason that I showed this Bose-Hubbard Hamiltonian, that this is the Hamiltonian of the system. So this you can, if you put 2-3 excitations, then you have to consider these higher levels. It gets difficult to read them, but if you have 5 excitations, when you have enough coherence and whatnot, they could be all, according to this, they could all pile up on a given nonlinear resonators eventually.
Nicolas.
You You said that you tune the qubits with the AC star defect, right?
No. The tuning of the qubit is super simple. There are so this is one junction, but here is two junctions, here and here, and they are forming a loop. And you can put a DC voltage. Essentially, you can think about bringing a magnet close by. You pass a current in this line. Hard to see. This is the wire that passes a current in here. As you pass the current, you change the phase relation in here, which essentially changes critical current, and it changes inductance, and eventually changes resonate. So you can pass currents, and you can see the resonance frequency of this qubit come up. What I said is that to read the state of this qubit, you capacitively couple, passively couple it to a resonator. This is 8 gigahertz resonator, let's say. But if this qubit is occupied, the AC star shift out to this qubit makes this to be 7998. So this 2 megahertz shift in the resonance frequency of this one can be tested, can be extracted from that.
Any other question from the audience? Not seeing hands. So let's thank Pedram Roushan again for the Then we should have some pictures ready in the kitchen, so we can keep discussing the nice ideas.
No worries. No worries. Thank you.
Thank you. I had a second question also in this line of other levels. So there are these ideas of using the oscillators rather than the qubits, like this, and then encoding. So using this
right.
variable space and then encoding qubits.
Yes. No. We don't work. I think you have to. Please about. That's more really on Yale School of Thought.
But is this? So I heard something saying that yes.
Tienes ahí, Catherine.
Sí. Es,
Te digo para que lo vaya desenvolviendo, está ahí todo.
sí, ahora empezamos. I was wondering, is this because people saying the oscillators are better than the qubits in some cases?
Well, not these ones. These ones are meant to be a little leaky, so we can read the state or information gets out of them. But if you design them that way, it could be because making an aluminum island is probably simpler than making an aluminum oxide aluminum junction. Yeah.
Okay, so you see it like a legitimate.
Of course. I mean, they have good results and all that.
And the question in this that I had, I'm not sure that I was completely clear, was this. As I understood, you do a digital simulation of this Heisenberg dynamics.
Yes.
And in the atomic physics experiment, they do an analog. Heisenberg.
Yes. And there is a paper by Tomasz Prosen, which says that for this universality class and for the bound state, they are all the same.
All the same. Okay.
The bound state, right? So the integrability of the